So let's just jump right into problem number 1. I'm going to write down in words the name of the name of the elements in the compound, and we're going to go from there. So what if you combine gallium and the element fluorine? Gallium and fluorine. What does that combine to make? Well, what is the chemical symbol for gallium anyway? That's not one that we use too much. So if we go over here and take a look, gallium has symbol Ga. Let's see where that is. Gallium is right here, symbol Ga, and fluorine is symbol F. So what we have here is gallium, which will be capital Ga, and then we have F. Now, what are the ions that these things like to form? So fluorine is pretty easy because it just wants to gain 1 electron, so it'll have a -1 charge. What does gallium want to do? It looks confusing with all of these elements here. You might start counting them, but then you recognize it's in the same column as aluminum. Aluminum has a +3 charge because it wants to lose 1, 2, 3 electrons. So because it's here, just look at the column it's in. It's going to want to gain or lose the same number of electrons as this column. So gallium wants to lose 3 electrons, just like aluminum. So what you get is a gallium wants to form an ion with a +3 charge because that's losing 3 electrons, and fluorine wants to gain an electron like this. So once you have this in place, you can just do the little crisscross like this, and then you can say that Ga has a subscript of a 1 that comes in there. We don't need to write that. And then fluorine, when you move the 3 down, has the subscript of 3. So gallium fluoride is what we're going to call this later. We're going to have a separate lesson on how to name these things. So don't worry too much about the words, the name for the words, but it's going to be called gallium fluoride, and this is the formula for that, gallium and fluorine. So again, when we get this into the final state, we want to check and make sure, is this the lowest ratio? Because we always want the formula unit for these ionic compounds to have the lowest ratio. This is not really able to be simplified with a 1 and a 3. We can't make it any smaller by dividing, so we're done with this one. All right, let's take a look at part B, and let's look at lithium and hydrogen. Lithium and hydrogen. Well, we look on the periodic table, we're reminded that lithium has a symbol Li, hydrogen has a symbol H. All right, now in general, what are they going to want to do? So lithium is going to want to lose an electron to look like helium, so it's going to be a +1. Now hydrogen is a little bit of a weird element because in some cases it likes to gain an electron, and in some cases it likes to lose an electron. We put it over here in the metal category, even though hydrogen is clearly not a metal. It behaves more like a non-metal. But the point is, hydrogen can do different things. Since it's coming into contact with lithium, lithium for sure wants to lose an electron. So lithium is going to have a charge, since it wants to lose 1 electron, of +1, right? And because of that, you kind of know how hydrogen is going to behave. It's going to want to gain the electron then to look more like helium. So in this particular case, hydrogen is going to want to have a -1 charge. But in other situations, hydrogen will lose an electron and be +1. So now that we have this situation in place, we can do the crisscross as usual, and we can write down that lithium has a subscript of 1 and hydrogen has also a subscript of 1 once we do this, and you have lithium hydride. We're going to talk about how to name these things later, but that's going to be the name, LiH. All right, let's take a look at the next one. All right, let's say that we're told that aluminum is going to combine with iodine. Right? So we look at the periodic table, we recognize that aluminum has a symbol Al, and iodine has symbol I. So what charges do they want? So iodine is the easiest. Iodine is here, it's going to want to gain 1 electron to look like xenon, and aluminum is here. Now, it's not going to gain all these electrons, instead it's going to lose 1, 2, 3 electrons. So aluminum loses 3 electrons, and iodine gains an electron. So iodine gains only 1, but aluminum actually loses 3 electrons, so it is going to have a charge of 3 plus, or +3 there. So once you have that in place, then you can, of course, do the crisscross here, and you can say that you have Al1 coming from here, and then iodine with the number 3 right here. So Ali3. Now, aluminum iodide is what this is going to be named later when we learn how to name this. So we have more problems to do, but before we go any further, let's just double check. We cannot simplify this any further into a lower ratio. 1 to 3 we can't simplify, just like we can't simplify this any further or this any further. So that's basically why we stopped. But never forget why the crisscross thing works. What this is saying is that because every one of these aluminums has a +3 charge, and every one of these iodines has a -1 charge, I need 3 of these things, which are each -1, to give me an overall -3 for the iodines. And that -3 is going to combine with only one of these, which has a +3, to make a neutral formula unit. So that's why you need 3 iodines. You need 3 of them because iodine only has a charge of -1. You need 3 of them to make -3 to kind of neutralize the aluminum. Remember, the reason it's neutralizing and combining like this isn't because it wants to, it's because the electric force is so strong. If there's ever a net charge, then it's just going to attract something else that sticks to it and then begins to neutralize it. So basically, if you envision one of these +3 ions out there, it's going to attract the first iodine, but then it's still going to have a charge of +2. Then it'll attract the second iodine, and it'll still have a charge of +1 overall. Only after attracting the third iodine to it, then overall this looks like a charge of 0, and it stops attracting more stuff. And this is not a molecule. Remember, it's a formula unit, which is the smallest ratio in a gigantic grid of these things that are bonded together in a lattice, in a crystal lattice. But the smallest ratio is 1 atom of aluminum to 1 atom of, or 1 iodine ion. All right, let's do the last one of this type, which will be combining potassium with, what are we doing? Sulfur. Now you'll learn these over time. I remember them. I'm trying to teach you by osmosis also. Potassium has symbol K and sulfur has symbol S. What charges do we want here, or do we have? So potassium is here, means it's going to lose 1 electron to look like this. And what was it? Potassium sulfide, right? We're going to gain 2 electrons here. So sulfur wants to gain 2 electrons, and potassium wants to lose an electron. So the sulfur will have a charge of 2-, and the potassium will have a single positive charge because it loses a single electron. And then, once we do this, we find that the potassium, the 2 comes down, has a subscript of 2, and the sulfur has a subscript of 1, and this is the final answer, K2S, potassium sulfide. We're going to learn how to name these later, but basically the second element gets an IDE at the end. All right, now again, you need 2 of these potassiums, each with a +1 charge, in order to neutralize the single sulfur atom, which has a charge of -2. That's why it's K2S. All right, the next problem is a little bit different. It's kind of a fun problem, I think. It goes like this. An unidentified element reacts with bromine to form an ionic compound of the formula XBr, where Br2, where X is some unknown element. Identify the element and give its chemical symbol if it has 86 electrons. So you're basically given a lot of clues, and we have to figure out what an unknown element is. So basically what we have figured out is that from the problem statement, this thing is going to have some form of some unknown element combining with Br, but there's got to be a subscript 2 right there. And so how do we figure out what this is and what the charge on it is and so on? So you have to work backwards. You don't know what this element is. That's what you want to find out, but you know what bromine is. So if we go to bromine and just kind of write it down here and put X kind of here, then what we know is that bromine is always going to form a charge of -1. It always wants to form a charge of -1. So in this case, what we're going to assume is that bromine always has a -1 charge, but basically it's Br2 right here. So in this situation, bromine has an intrinsic charge after it gains the electron of -1, but there's 2 of them. That means that this entity right here has a charge of -2, an overall charge of -2, because there's 2 of them here, and each of the bromines is -1. Now to balance it, it needs to bond with something here. The subscript is only a 1, so there's only 1 of them, so the charge on this thing has to be a +2, and we figure that out by looking at what it's bonding with. because we have two bromines, and we know that every one of the bromines has a charge of -1 from the periodic table, the overall charge on these bromines as a group is -2. To balance that, I have to have an unknown element that has a +2 charge because there's only one of them here. And this is what you don't know from the problem statement that we had to figure out from it. So what we need to figure out is what element can have a charge of +2 after it loses some electrons. But the problem actually tells us, it says, if I can get there and get the exact wording, it says, identify the element and give its chemical symbol if it has 86 electrons. 86 electrons. Now think about it. The actual element, once it's in the bonded state with in this ionic compound, it has a charge of +2, right? The only way it can have a charge of +2 is if it loses 2 electrons. Now it tells me right here that the actual element here in this state, it has 86 electrons. And that means the neutral form of the atom must have 88 electrons. It has to have 2 more. So in other words, I have 86 electrons in the ion, and so I must then have 88 electrons in the neutral atom. Because, why? Because this atom, whatever it is, must have lost 2 electrons to give me a +2 charge. So I had to have 88 electrons in the original atom, because in the bonded version, in the ion here, I have 86 electrons. And so in the neutral atom, if I have 88 electrons in the neutral atom, I must have 88 protons, right? To balance the 88 electrons in the neutral atom. So you look at the periodic table, what has 88 protons? The atomic number 88 is down here. That's radium, Ra, radium. So you know, basically, you know that this thing has to be radium, RaBr2. This, I'm not going to circle it because it's not the answer, but this is what the unknown element was. Because radium has 88 electrons, right? We get that from the periodic table. Radium also wants to form a +2, right? Because it wants to lose 2 electrons. So that makes sense. And we're told that in the bonded state, it has 86 electrons. So in the neutral version, it must have 88. And so 88 is the atomic number, and that's what it is. And this is why it formed. So what is the unknown element? The unknown element is radium, and the charge on it is +2 in the ion version. So that's basically the answer to the question. The compound here that we had unknown as XBr2 is really radium Br2. The +2 goes here, the -1 goes here. All right, now for the rest of this lesson, we're just going to go through kind of like a lightning round where we write down the chemical formula for a bunch of ionic compounds. Some of them involve polyatomic ions and some don't. But you'll see that it's exactly the same process no matter what we do. So let's take a look, for instance, if I tell you ahead of time that potassium has an ion charge of +1, and I'm going to combine it with chlorine that has a charge of -1. Sorry, that's carbon. Chlorine is Cl, negative charge. First of all, do these make sense? Well, potassium does want to lose 1 electron, and chlorine does want to gain 1 electron, so these charges make sense. And if I tell you that a potassium ion combines with a chlorine ion, then you just do your magic like this, and you write down KCl, because the 1 goes here, the 1 goes here, and this is a 1-to-1 relationship. I cannot simplify it anymore, so that's the final answer. All right, what about, I guess I'm going to have a lot of these, so I'm going to try to keep them separated. What about potassium as a positive ion combining with the hydroxide ion, OH, negative? Now, let's go to our table of polyatomic ions. This is not an exhaustive table, but it's to get us started. When we go over here to the anions, you see there's a lot of anions. Remember, a polyatomic ion is just a group of nonmetals that are bonded together. We're going to learn more about why they do this later when we talk about the electrons, but they have an overall charge. So a polyatomic ion is just many atoms that together behave as an ion. In this case, when an oxygen and a hydrogen come together and the overall unit has a charge of -1. You are not supposed to be able to predict and understand why these things have the charges they do at this stage. You're not. I'm just giving you a table and telling you that this thing called a hydroxide ion exists when oxygen and hydrogen come together and the overall thing has a -1 charge. So I've just written it here, OH, and it has a negative charge. But you treat it the same way because see now you have a positive ion and a negative ion. It's just that the negative ion is a little more complex than in the case of a single element. But you still do the crisscross on it. It behaves in the same fashion is what I'm trying to tell you. And so the potassium gets a subscript of 1, and the OH as a unit, I don't need to put parentheses if there's a subscript of 1, but you can think of it as parentheses with a 1 down here because the 1 goes there, but we don't really write it like that. We write it as KOH, right? This is called, as we're going to name them later and learn how to name them, potassium hydroxide, because this OH behaves as a unit called a hydroxide ion. That's why it's called potassium hydroxide. All right, what about potassium ion bonding with another ion, which says CO3 with a charge of -2. What is CO3 with a charge of -2? So down here you can see this is called a carbonate ion. So these all have names, and I don't really feel like getting into it because I don't think it enriches you that much. But these ions have names for a reason. Carbonate, sulfate, sulfide, they all have little naming rules, but at the end of the day, all you're going to do is look in a table and you know what the name of it is from a table. That's what we're going to do in this class. So you go here and you say that CO3 with an overall charge of -2 is called a carbonate ion. From your point of view, I've already given you what the ion is. So this goes here, and then this charge goes here. And so what you get is the potassium takes on a subscript of 2, and then since this is a 1, you just write it as CO3, and then this is an overall subscript of 1 out here. So you don't have to write the parentheses. So K2CO3. All right, moving right along. Moving right along. Let's take a look at, once again, the potassium ion combining with PO4, which has a charge of -3. So in our table of polyatomic ions, PO4, here it is, PO4 -3 is called a phosphate ion. So this is going to have the word phosphate in the name when we write it down. And so what we see is we do a crisscross right here and like this. So you have the potassium taking on a subscript of 3 and the PO4 taking on a subscript. If you had parentheses, you'd put a 1 on the outside, but we don't need to write it. So you write it as K3PO4. All right? I told you we're just going to do a bunch of these things, so let's keep on going. What if we have something a little bit different? So all of these had potassium for the cation, right? And then we had different anions, which in some cases were polyatomic ions. Here we're going to change it up, and we're going to tell you that we have an ammonium ion, NH4, which has an overall charge of +1, combining with chlorine, which has a charge of -1. Chlorine always wants to have a charge of -1 from the periodic table. NH4 is a polyatomic ion right here called ammonium, the ammonium ion. So this will be called ammonium chloride. When the second ion, the anion, gets an IDE if it's just a single element like that. So again, we're going to do naming later. But you see this ammonium ion is 1 nitrogen connected to 4 hydrogens where the overall unit has a charge of +1. Again, you're not supposed to know why it has a charge of +1. That comes later because all of these polyatomic ions, they have their charges because of the electron sharing going on, and it's way beyond the scope to understand why. For instance, why does the permanganate ion have a -1 charge? Why does the chromate ion have a -2 charge? We're going to talk about that stuff later. But for now, I'm telling you what these ions are, and so all you have to do is say, okay, we have opposite ions, they're going to attract each other ionically, and so we do the crisscross, and we figure out that NH4 as a subscript of 1, so we don't need to write the parentheses with a 1. I mean, you can if you want to. You can put a subscript 1 there, and then you could put Cl, and then this 1 goes here, subscript of 1. But we don't need to write all this. We just say NH4Cl. NH4Cl. Ammonium chloride. All right, let's take a look. Again, the ammonium ion, NH4, which has a +1 charge, combining with a hydroxide ion, which is the same one we used up here, which has a -1 charge. So now we have 2 polyatomic ions interacting with each other. One of these polyatomic ions acts as a unit having a positive charge, and the other one acts as a unit having a -1 charge. So of course they're going to attract each other ionically. So they're ionically bonded together. So this one goes here, and what do you get? NH4 with a subscript of a 1, and then OH with, again, a subscript of 1, and so this is what you get, NH4OH. All right, let's take a look. What did we have? What if we have NH4 with a positive charge interacting with that carbonate, CO3 with a -2 charge. Remember, CO3 with a -2 charge, we call it a carbonate ion. So this would be ammonium carbonate, right? So what do we have? Do the crisscross like this, and then we have NH4. But now this 2 has to come down here. So to make it clear, you don't want to put a 2 right next to the 4. It looks like 42. So you wrap it in parentheses with a 2 here. This means that we have 2 of these ammonium ions here. And then we have CO3, and the 1 comes down. And because there's a 1, I don't need to put parentheses. I just write it as NH4 parentheses 2 CO3. This is the final answer. All right. What about the last one for ammonium? NH4, positive charge, interacting with this phosphate, PO4, 3 negative, or a -3. Remember, that is the phosphate ion. So you kind of learn them by, by doing, right? You learn them by using them. You don't learn them by studying a table. That's not going to get you anywhere. So this goes here, and then this 3 goes here. So you have NH4. The subscript needs to be a 3, so we need to wrap this in parentheses and make it a 3. And then the PO4, the subscript of this ion, has to be a 1, so we don't need any parentheses. So we write it as NH4, parentheses 3, and then PO4. All right, so we're actually halfway done. We have a few more here. Now, instead of, notice the cations, I've used potassium, and then we used a bunch of ammoniums. Now we're going to have another cation of magnesium. Magnesium, I'm going to tell you ahead of time, has a charge of +2. Let's combine it with chlorine, which has a charge of -1. Let's first see if these make sense. Magnesium having +2 makes sense because magnesium is here in the table, and it's going to lose 2 electrons. That's going to give it a +2 charge. Chlorine is going to have a charge of -1. So that's why we have the charges here that we have. All right, next, the 2 is going to go here, the 1 is going to go here. So magnesium, a 1 comes here, and then Cl2 from right here. So MgCl2, that's the final answer for the ionic compound. All right, on this board, we're just going to do 3 more, and then we have a little more, and then we'll be basically finished. So what if magnesium with a +2 charge combines with this hydroxide, which we've been using for the other elements, or for the other instances here. So again, magnesium +2 charge, that comes from the periodic table. And the hydroxide ion, we've been using it before. This comes from our table of polyatomic ions. It's just OH with an overall -1 charge. So this goes here, this goes here. So the magnesium has a subscript of 1, and the OH now has a subscript of 2. So I have to wrap it in parentheses because the 2 goes down here. So we have MgOH2. So you see in the previous examples when we used hydroxide, we didn't have any parentheses around the answer. We didn't have any parentheses around the answer because the subscript was a 1, right? But in this case, because the subscript was a 2, I needed to wrap it in parentheses to show that I have 2 hydroxide ions bonded to a single magnesium. Remember, if magnesium has a charge of +2, then I need 2 of these hydroxides, each of them having a charge of -1, in order to neutralize this thing. That's what an ionic compound is going to do. All right, next. Let's say that I have magnesium with a charge of +2, and that's going to interact with this carbonate, CO3, which has a charge of -2, just like this. So these are coming together, so we're using the carbonate again. So what do? This crisscrosses like this, and you have Mg. Now the 2 goes down here, and because the 2 goes over here, applying to that carbonate, I actually need 2 of them, so I need to wrap it in parentheses to show that I have 2 of these carbonates. So I have Mg2CO3 and you think you're done, but then remember I kept telling you in the beginning, I said, hey, when you do the crisscross method, you always want for ionic compounds the formula unit to be the lowest whole number ratio. And in every one of these cases, we already arrived at the lowest whole number ratio. You had a 1 and a 1, a 1 and a 1, a 2 and a 3, a 4 and a 1. These are already lowest whole number ratios, but this is the first time we have a 2 and a 2. I can reduce this by dividing each of these numbers by the number 2, and I will then get Mg 1 CO3, again 1. So basically I divide both of these by 2 and I get a 1 and a 1. So really the formula unit is the lowest ratio, which is MgCO3, which is magnesium carbonate, right? So this is the correct ratio. It is 2 magnesiums for every 2 carbonate ions. However, for ionic compounds, since there's no molecule, we just want the lowest ratio between what we're talking about. So it really should be 1 to 1. This is the correct answer. All right, last one. What if we have the magnesium ion interacting with the phosphate, PO4, -3. So we do the crisscross, and what do we get? We get magnesium with a 3 coming down here, phosphate, so put PO4. You need to wrap this in parentheses because a 2 is coming here. Now again, these are already in a lowest ratio. I can't divide them by anything to make them simpler, so this is the final answer. All right, we are almost done. We have a few more, our last one. Here, what if I tell you Fe, which on your periodic table, Fe is iron. Iron has a +3 charge. Now let it interact with a chlorine, which has a -1 charge. Chlorine always has -1. Iron can take on different charges, but I'm telling you, in this case, that it's a +3 charge ion. So you do the crisscross like usual, you get iron, a 1 comes down here, and then Cl3 like that. So iron chloride. Actually, we have to talk about the ion charge. When we have multiple charges possible, we get into that more when we do the naming. So it's not exactly iron chloride. There's some other stuff we have to talk about, but that's essentially what it is. We do have to talk about the charge in the name because the transition metals that are in the center of the table, they can take on different charges. So depending on the charge they take on, we have to when we get to the naming lesson, I'll show you how to handle that a little bit more cleanly, I guess is what I'm trying to say. So FeCl3. Next, we have iron with a 3+ charge interacting with a hydroxide ion, OH negative. So we do the same thing. So this goes here, this goes here. We have iron. The -1 goes here, so a 1. And then OH, I need to put parentheses around it to make it a 3. The 3 goes here, the 1 goes here, and we have FeOH3, like this. All right, almost done. Let's take a look at a +3 charge on an iron, and then carbonate, CO3 with a -2 charge. All right, same thing. They're going to attract each other. And so you're going to have Fe, the 2 is going to go down there, the CO3, you need to make it a 3 because the 3 goes down there. So Fe2, CO3, parentheses 3, that's the final answer. And here's our very last one, I promise. If I have iron with a +3 charge, and it's going with the phosphate, PO4, and that's 3 negative, like this. And this one we're going to have to be careful of. Let's see. Let's bring it over here. You're going to have Fe, the 3 goes down here, and then the phosphate, PO4, and then you're going to have a 3 down there. So this is a case where once we do the crisscross, we see we have a 3 and a 3. This is not the lowest ratio because 3 to 3 is the same as 1 to 1. I can divide both of these by 3. So what you really have is iron with a 1 there, and then PO4. Because you divide both by 3, and you get 1 and 1. So Fe, PO4, again, with both a subscript of a 1. So this lesson was just giving a little more practice with writing down ionic compounds. I know it was a lot of repetition, but that's what I want it to be. I want you to look at ionic compounds and know how to write down the formula all the time. Because when we do chemical reactions, that's what you're going to have to do, and it's going to be like second nature. I mean, you're going to need to be able to do that. So anytime you have a metal combining with a non-metal, that's going to be an ionic bond. If you have a metal combining with a polyatomic ion, a negative polyatomic ion, again, it's going to be an ionic bond. So that's what we're talking about and just getting practice with it. Again, the polyatomic ions that we learn in this table, you are not expected to basically have them all memorized and their names and their charges. I mean, you can do that if you want, absolutely, but I don't expect you to know that. I just need you to know that there are some ions that are formed with multiple atoms. They're almost all nonmetals. If you look at all of these polyatomic ions, they're all nonmetals bonded together. And we're going to learn later that they're covalently bonded together. The electrons are being shared, and so it's kind of difficult ahead of time to predict what charge will be on these things. So that's why we give you a table and we say, hey, these things form. There's a thing called a hydroxide ion, very common, has a -1 charge. There's a thing called a nitrate ion, very, very common, NO3 with an overall -1 charge. And once you know what those polyatomic ions are, the common ones, which are on this table, then you can see how to combine them with other cations, metals, from the left-hand side of the table, or ammonium, which is the only polyatomic ion we have that's positive, and we can form ionic compounds with them. So practice these, and then follow me on to the next lesson where we're going to focus on how to name these ionic compounds. Learn anything at mathandscience.com.